Hi. Today we're going to be taking a look at some of the questions from paper 2 and paper 3 of some GCSE exams, mostly problem solving. Let's start with question number 1. Two children, A and B, are sitting on a seesaw as shown in the figure below. The seesaw is balanced. They're asking us to basically use the equation of moment to calculate the moment of child B about the pivot of the seesaw. Now, before you go ahead and do anything, let's write down the information that we have been given. Force is simply going to be equal to 280 newtons. The distance of the child, which is child B, to the pivot is 90 centimeters. Now, 90 centimeters is essentially equal to 0.9 meters. Don't forget to convert that because the unit has been given in Newton meters, actually. Now, we know that moment is equal to force times distance, and the formula has actually been given to us. So simply multiply 280 by 0.9, which is 9 over 10. 9 times 8, essentially going to be 9 times 28, which is 252 Newton meters. That's the answer to question number 1A. Let's move on to B. Use the idea of moments to explain what happens when child B moves closer to the pivot. So let's imagine child B actually moves a bit closer to the pivot. If that happens, let's say, for example, he moves 5 centimeters closer to the pivot. He's now 85 centimeters away. Whenever the distance decreases, the moment actually also decreases. And it's actually vice versa. So if you increase the distance, moment increases. So you can write that moment decreases because distance has decreased. Distance has decreased. Let's move on to another question now. 2, it says, figure 1 shows a piece of apparatus called a current balance. Okay, let's take a look at this one. So we have a magnet here. Okay, it's been labeled, and we have a bit of a circuit in a way. We have a battery here and what appears to be a variable resistor, an ammeter, and a switch. Okay, when the switch is closed, so when this thing is closed, obviously we have an electrical current. The part of the wire labeled X, this part, experiences a force and moves downwards. It goes down, so that's being attracted to the magnet, basically. What is the name of the effect that causes the wire X to move downwards? The name of that effect is simply known as motor effect, and that's basically when the current from the wire actually creates a magnetic field around itself, and as a result is now going to be attracted to the magnet itself, and that's why part X actually goes down. It says, suggest one change you could make to the apparatus in figure 1 that would increase the size of the force that the wire X experiences. Now, we know that the size of this force is calculated from, it's calculated from B, which is the magnetic flux intensity, multiplied by the current, multiplied by the length. So, essentially, force is equal to BIL, where B is measured in Teslas. It's the magnetic flux intensity, magnetic flux. I'm just going to write magnetic flux. I is obviously the current, which is measured in amperes, and L is the length of the wire, which is measured in meters. Now, and force obviously measured in newtons. You can increase the amount of force by simply, manipulating any of these 3 variables. So you can, for example, increase the magnetic flux intensity, which would mean basically using a stronger magnet, or you can increase the current, which would mean using basically a stronger battery. So either by increasing the current, or using a stronger magnet. Use a stronger magnet. All right, let's move on to the next part of the question. Part C says, figure 2 shows a small weight placed on the insulating bar, which makes the wire X go back and balance in its original position. Okay. They're saying, they give us a bunch of information. The wire is 5 centimeters long. The current is this much. So current is 1.5 amperes. The length of the wire L is 5 centimeters. The small weight causes a clockwise moment of this much. So the moment is 4.8 times 10 to the power of -4 Newton meters. calculate the magnetic flux density. All right, so basically they're asking us to calculate B, or the magnetic flux density. F is equal to BIL. But unfortunately, we have not been given the actual force. If we rearrange this equation, we know that B, or the magnetic flux intensity or density, is actually equal to force divided by current multiplied by the length. However, we don't really have the force. We have moment. But we do know, step one, that moment is equal to force times distance. And we've actually been given the distance of, from the pivot, which is 8 centimeters. So this is 8, and moment has obviously been given. Force is simply going to be 4.8 times 10 to the power of negative 4 divided by the 8 centimeters of the distance. Basically, what I did here is I rearranged the original equation. I got that force is simply moment divided by distance. And I'm dividing the moment by distance now. So if you divide 4.8 by 8 centimeters, don't forget to convert the centimeters into meters. So basically multiply it by 10 to the power of negative 2. If you do that, divide by 8 times 10 to the power of negative 2, you're going to be left with 6 times 10 to the power of negative 3 newtons. Now, step 2 of this question is to simply put this back inside. B is equal to force, which is 6 times 10 to the power of negative 3, divided by the current, which is 1.5 amperes, multiplied by the length, which is 5 centimeters again. And again, don't forget to convert centimeters to meters. All you have to do for doing that is just multiply by 10 to the power of negative 2. So times the length, which is 5, times 10 to the power of negative 2. All right, so 6 times 10 to the power of negative 3 divided by 1.5 times 5 times 10 to the power of negative 2. We're going to be getting 0.08. Now, as you can see, they're saying the magnetic flux density. How much is that going to be? Obviously 0.08. What's the unit? Tesla. All right, we're going to end this part of the video for today at question number 2. We're going to be continuing this on for the next video. Stay in touch and don't forget to subscribe. Goodbye for now.